a little bit off, because actually we forgot that there was also 1 there. This is going to be ln, upper bound. But then you have 1 plus that. So it's 1 plus ln will be the upper bound. So of 20, we had what? What's ln of 20? Who said it was 3. So in reality, we're looking at 4. We're looking at 4. All right. I don't know what that is. Oh, let's see. All right, so we're going to look at this one right here. So the online hiring problem I mentioned to you last time, what we're going to do is we're going to look at a set of candidates, and what we're going to do is we're going to basically only interview a few of them early on. We're going to take a random selection of K candidates. Okay? And we will settle for hiring a candidate close to the best. Close to the best. We may hire the best, we may not. So we are risking. But if we don't hire the best, we also probably won't hire the worst. Right? For example, let's say we have 20 candidates and we interview 3 of them. We will hire the first one that's better than the best of the 3. What's the worst that the best of the 3 could be? What's the worst possible quality out of 20 that the 3 could be? What could their quality value be?
17.
Well, we're counting the quality going up, so 1 is the worst and 20 is going to be the best. So the worst situation could be 3. So, is that very likely that 3 will be the best? How likely is it? What's the probability of that? Well, the probability of that is the only way that 3 is going to be the best is that if 1, 2, and 3 are in the 3. And how many ways can that happen? How many ways can we start with 1, 2, 3 to start with? 6 ways. There's 6 ways that can happen out of a total of how many sequences? 20 factorial. So let's do the math. Let's do the math. So what we're going to do is we're going to take 6. That's going to be a very small number. We're going to take 6 and we're going to divide it by 20 factorial. And the probability of that happening is 0.00000000 17 times. 17 0, 0.017 times. 2466. Yep.
The worst thing we could hire would not be number 4. We could hire, we're ahead of 3.
Correct. So if, right. So now, if 3, quality 3, is the top of the first 3, then the worst we're going to hire is 4. And that will only occur if 4 immediately follows the first 3. How many sequences do we have of that? Well, we have 6 sequences of 1, 2, 3 go, right? Then we have to fix 4. And then we have 16 factorial sequences following that. So the probability that we hire the 4th worst candidate is very, very low. I'm not going to even crank up those odds, but it's going to be very, very low. The bottom line is we're trying to choose a value of k. K is 3 right now, but I'm going to let k float around so that we want to find the equation which maximizes the value of k. Okay, so we're going to hire once, and once we hire the person, that's it. All right. So what we want to do is minimize number of candidates interviewed and maximize the quality of the hired candidates. That's what we want to do. So this is our approach. This is our approach. We give each candidate a unique score, 1 through n, 1 through 20, whatever it is. After seeing j applicants, we know the highest score from applicants 1 through j. We do not have the scores of the n minus j candidates, which follow them. So we will choose a k less than n, where we interview the first k applicants, but don't hire any of them, and we keep track of the maximum score of the employees 1 through k. We will hire the first applicant with a higher score than the maximum score of the first k. If score max was the higher overall, we hire applicant n. That's a very interesting situation right there. Number 4 is the most interesting one. Do you understand fourth criterion? What does it mean? What does it mean, last one? Do you understand that? If score max was highest overall score, we hire applicant n. Do you understand that?
Yeah, because we interviewed all the best people in the first.
Not the best people, the best person. The best person was in that little group of k people. And guess what? He was not hired. So now once we go past those k people, we will never have anybody better than that. So by the time we get to the n minus first person, who's not better than the best, and we don't hire them, because we're hoping for something better, we will hire the last person. So every time the best person is in the group, we will not hire the best person. Does that make sense? Every time the best person is in the first K, we don't hire them, by definition. Now, what happens if the best person is in the K plus 1 through n? Do we always hire them? No. They have to come either immediately after the first K, or they have to follow people who are not better than the best of the K. So it's tricky. So the highest score overall was score max, was the best. We didn't hire that person, we just hired the last person because we have no other choice. We keep looking for that better person, but we don't cross them. So you could see that if K is very small, for example, out of 20, if K is equal to 3, what's the probability the best person is in the first 3? 3 out of 20, which is what? What percentage? What's 3 out of 20? 15%. So if there are 3 people out of 20, and we take the first 3 and use that as K, then there's a 15% chance that the best person will be in this group. So 15% of the time, we are guaranteed of not hiring the best person. And 85% of the time, we may hire the best person. If K is equal to 2, the probability, and the person was probably the best person in the first group of 2 out of 20. 10%. 10%. So there's a 10% chance we don't hire the best person if K is equal to 2. There's a 90% of the chance that the person is not in the first group of 2, and we may hire them. Maybe. So making the group smaller, making K smaller, makes it less likely that the best person is going to be in that group. Making the group larger makes it less likely that makes it more likely that the person is in that group. So we don't want K to be too big, because if K becomes too big, then a lot of the time, most of the time, the best person will be in the group of K, and we won't hire the best person. And we'll end up hiring the last person. What will be their quality? What do you think will be their quality? What will happen in that case? What will happen in a case where the best person is in the first K, and we hire the last person? What do you think is, out of 20, what do you think is the expected quality there? Yeah, what do you think will be the mean quality of the last person? 10. Why do you say 10? Because last position, everybody has equally likely chance of being there. There's quality 1, plus 2, plus 3, plus 4, plus 20. Add them up, divided by 20, you get 10. That'll be the average. 1 plus 20, 2 plus 19, equals 18. You add up all those pairs divided by the pairs, you're gonna get about 10.5, something like that. So if the best person is gonna be in the control group, we'll call it the control group, then we'll hire on average 10.5. But that's an average. It doesn't mean that we'll hire 10.5 on average, because if it's our company, we're only gonna hire one time. Averages don't mean much to us, do they? Averages don't mean much to us. It means that if 100 companies did that, they would hire on average a person with 10.5 quality value. But we might have gotten stuck with a person with second quality value. There's no way of controlling it, because we're only going to hire once. So averages are good, but we're only going to do this once, so the average doesn't really, it gives us confidence that that's expectations, means it's going to happen. Okay. So, so this is the algorithm that we talked about. I'm not even going to bother to show it to you. See it? Okay, so let's define our events. So then we can define our probabilities. So we're going to let m sub j be the maximum from 1 to j of score I. I is going to go from 1 to j, and the maximum of the scores from 1 to j of the score will be equal to mj. So mj is the maximum of the score of people from position 1 to position j. S is the event we succeed choosing the best qualified applicant. S is the event we succeed in hiring the best applicant. SI, this is interesting. SI is the event we succeed hiring candidate I when the best applicant is applicant I. So SI is the event we succeed when the best applicant is applicant I. So S is the overall success, the event that we hire the best. SI is the event that we hire the best candidate when the best candidate is the I candidate. Okay? Let's see if we can make this bigger. That's too good. Whoops. I don't like this at all. Any problems here? Good, that's where we want to be. Okay, that was good. We almost have it. Make it a little bit smaller. Okay, that's good. All right. So what's PRS? What does that mean? Probability of S, and S is the probability of hiring the best person. So the probability of hiring the best person is equal to the sum from 1 to n, as I goes from 1 to n, of probability of hiring the best person when the best person is the ith person. So you understand why it's from 1 to n, because we're interviewing a total of n people. However, how many of them are we not hiring? K, for sure. Guaranteed not to hire K. We're only going to, yeah, you're right about n minus 1. You're right about that, but that's not what I was looking for. So why is I to n PRSI equal to I equal to K plus 1 n PRSI? Because we're never going to hire them. So the probability of success hiring the best person is equal to the probability of hiring the best person when the best person is person I. Because if the best person is person 1, what's the probability of hiring them? 0. So the probability of hiring the best person when the best person is person 1 is 0. Why? Because 1 is going to be in the control group. If K is 3, then 2 and 3 are also going to be in the control group. So that's why the probability of SI from 1 to n can be written from K plus 1 to n. Because we're never going to hire this other one, their probability is actually 0. So the probability of success, this is the one right here, PR of S sub I. The probability of success when the best applicant is the ith one requires two things to happen. This is important. The probability of successfully hiring the ith candidate being the best requires two things to happen. Number one, the best candidate must be the ith candidate. Okay? Okay? And so we write that as an event B sub I. B sub I is the event when the best candidate is in ith position. The second thing that's very, very important in order to hire the best ith candidate is that the algorithm will not select any applicants in position k plus 1 through I minus 1. Does that make sense? So let's break it down again. So we have 1 to k. And now after k, we start with k plus 1. So k plus 1 is the first person we might hire. Suppose I is out here. Therefore, and let's say I is the best person. So in order to hire this best person, what has to be true? B sub I, let's say it's true, let's say that the ith person is the best. The next thing we have to do is we have to make sure that the score will not select out, people. How do we not select people from k plus 1 to I minus 1? This is the ith person, it's I minus 1. How do we make sure of that? The people from k plus 1 to I minus 1 must have a lesser score than the maximum in k. So the bigger k is, the better chance we have of really bringing that threshold up. But the better chance we have of losing the top candidate also. See what I'm saying? So we are doing two things. By making k bigger, we're working against ourselves. Because it's decreasing the chance of hiring the best person, but it's increasing the chance of hiring a good person. But it's also increasing the probability of hiring the last person by default. So we need to sort of find out when is k going to give us the optimal behavior. That's what we're looking for. So this will occur when the j value, j index, which is the people at k plus 1 through I minus 1, when their score is less than the best score. If that happens, we will hire candidate I. So now we will define event O sub I. O sub I is the event that none of the candidates in position j are chosen, where j is k plus 1 through I minus 1. So O sub I is the event that none of the people in positions k plus 1 to I minus 1 are chosen. And B sub I is the best candidate is waiting in ith position. Okay, so now we want to put some numbers to that. Let's see if I can move my, what is going on with my computer? And, whoops. I'm not sure that's correct. Oh, how do you know when to stop? Obviously,
Based on your cursor.
oh. Touchscreen still works, just don't touch it when the glass goes into your fingertip. That's the key. Successful. Okay. So BI is an event and OI are events. They're independent events. What is BI again? That's the event that the best candidate is in position I. And OI is the event we do not choose people in position k plus 1 through I minus 1. Okay? So these are independent events. And this makes our probability a little bit easier. So the probability that we choose SI, we hire SI where SI is the best, is the probability that BI and OI occur together. And when events are independent, the probability of independent events is the product of the probabilities of the events. For example, I'll give you an idea of independent events. if I take a, you know what a die is, right? Like a dice, but only one is a die, I roll it, what can I roll? Okay, I'm gonna roll 1 to 6. So I'm gonna get 1, 2, 3, 4, 5, or 6. So let's say I rolled a 3. Now I'm gonna take it again, I'm gonna shake it, I'm gonna roll it. Is the probability of the fact that I got a 3 on the first roll, does that change? What is the probability that I get a 3? What's the probability that I get a 3? Okay, how about if I roll it a third time? So they're independent events. Independent events means that one occurrence of one doesn't mean the other one is going to be happening. So that means the probability of the intersection of two events, the probability that both events happen, is equal to the probability that this one happens times the probability that that one happens. Now, the probability that the ith person is the best is simply 1 over n, because we are assuming equally likely location of everybody within the sequence. So probability of b sub I is 1 over n. Now, OI, the probability of that one is the best scores in candidates 1 through I minus 1. 1 through I minus 1 must occur in positions 1 through k, and it's equally likely. So the probability of O sub I is going to be k over I minus 1. See if that makes sense to you. So the probability that we do not hire in positions k plus 1 to I minus 1 is k over I minus 1. Remember, I minus 1 is everybody before the ith person. Everybody before the ith person is I minus 1. What's k? K is the control group. So let's say the control group is 3. Let's say I is equal to 12. Let's make I equal to 11. Then the probability of OI is 3 over 10. 30%. Why 30%? %30 chance what? So the probability that I don't hire k plus 1 through I minus 1 is equal to k over I minus 1. So again, think of I equal to 11, k equal to 3. Control group is 3. 3 over 10. 3/10. There's a 3/10% chance that we don't hire in positions 4 through 10. Why?
Your best candidate is a 1 through 3.
The best candidate is in 1 through 3. And there's three possibilities out of 10. Equally likely. So 3 out of 10 is the probability, what? Of having a better candidate in the control group than in k plus 1 through I minus 1. 3 out of 10. 3 in the control group out of 10. They're equally likely. So there's a 30% chance. Okay. So therefore, the probability of SI is equal to k divided by n times I minus 1. We need to find this probability for all. So what is the probability of S sub I? Probability of S sub I is the probability of both of these occurring, right? So the probability of 1 is going to be 1 over n, 1 over n, and the probability of this is k over I minus 1. So this is just multiplying this by this. So it's k over n times I minus 1. We need to find this probability over all values of I, for all candidates. Why do we need that? Because, if I dare to change the page, I don't think I should, but because the probability of S will equal to the summation of the probability of all the S sub i's. This is the probability of S sub I. Oops. This is the probability of S sub I. And I'm going to sum that all over I. You understand? That's what I need to do. Okay, let's go to that. So, let's do the summation. So we need to add all the S sub i's together. So the probability of S, you understand that this is just S sub I, right? Probability of S sub I. So I'm going to sum it from k plus 1 to n. Why k plus 1 to n? Because It's 0 from 1 to k. Okay, good. So we're going to do that. So now how do we do that? First of all, the only variable that's changing is variable I is changing. So that means that k is not changing, n is not changing. They can come out in front of the summation. So what we have is k over n times the summation of 1 over I minus 1. Okay, and if we factor this, this is going to be 1 over I. This is simplified. I just simplified it a little bit. But we can, there's a few mathematical ways we can do it. But the bottom line is, so I still have k over 1, but now here, what I did was I simply changed the index from k plus 1 to k. So I brought the index down and down. So I brought the value of I to I plus 1 by up. I plus 1 minus 1 is I. So therefore, now the summation is exactly the same. Term for term is the same. Because the first value is going to be 1 over k, right? And what's the first one here? 1 over k plus 1 minus 1, 1 over k. Okay, so this is the summation we have to solve. But we know how to solve the summation. It's the same harmonic series, right? It's the same harmonic series. So we can use the same integral for a strictly decreasing series, as we just used in part 1, which is the ordinary hiring problem. Probability of s is going to be less than or equal to kn times this. And this is going to be approximated by the upper bound of this one. Because it's decreasing, we decrease k to k minus 1. Keep the upper limit the same, to make the width the same, 1 over x dx. It's going to be k over n. And it's going to be natural log of x evaluated from n minus 1 to k minus 1. So it's going to be natural log of the upper limit minus the natural log of the lower limit. The lower bound, by using, what's the lower bound going to be? It's going to be k over n times the integral from what to what? What's the lower limit going to be? That's the upper limit integral, right? Sequence is decreasing, so we can't start at k, because if it's decreasing, it's going to get smaller right away. So we want it to be getting smaller to the previous point. So therefore, we're going to take this back 1. So what's the lower limit going to go? Where's the integral going to start for the lower limit? Nobody? Decreasing sequence. So where's the lower limit? So the first rectangle looks like this, but the curve gets smaller immediately because it's decreasing. Well, you can start it right at k, and then you're going to go to n to make the same width. So when you get that, you get the probability of s is greater than or equal to kn, integral from k to n, and you can see you're going to have n minus k. This was the limits. Look at this. Look at this. So those are the limits. So, since we have a solution, this is a solution, for example, this is, in fact, this right here is the lower limit, right? This is the lower limit. What I'm going to do is take the derivative with respect to k. Now, you guys, we all know how to take derivatives. What's a derivative? Yeah. So what does a derivative do? Derivative shows us what? The tangent line to a curve. Right? So if I have a curve, y is equal to x squared, which looks like this. It's a parabola. The derivative of x squared is 2x. So that means when x is equal to 1, 2x is equal to 2. That's the slope of the tangent line. When x is equal to 2, 2x is equal to 4, that's the slope of the tangent line at x is equal to 2. To the curve. When x is equal to 4, it's going to be 8. So you can see that the derivative shows us the slope of the tangent line. What does it mean when the derivative is equal to 0? If the derivative is equal to 0, that means the derivative is what? Has a slope of 0. What's the slope of 0?
About line.
It's a horizontal line. Where is the derivative? What kind of curves do we have that have a slope of 0? Tangents. Well, if you look at a parabola that opens downward, at the top of the parabola, you see a tangent line? At the vertex, it goes 2, and after that, it starts going negative. If you have parabolas opening upward, then you can see that your tangent line is going to go like this, and eventually it's going to go to 0. It's going to start going positive. So if we take the derivative, which is the equation of the tangent line at any point in the curve, and we set it equal to 0, we can solve for the value of x at which the tangent is horizontal. Now, why is that significant? It's significant because if you have a curve that looks like this, the only place where the tangent is horizontal is at the max point of that parabola. So when you have a quadratic, which is second power equation, which is either parabola opens up or parabola opens down, when you set the derivative equal to 0, you can find out which value of x has the maximum point on that curve, or if it's opening downward, or if it's opening upward, which x has the minimum point. So that's what we're going to do. So d dk means the derivative with respect to k. And I'm using d dk because I want to make sure that you don't think n is the variable. It's not. K is the variable. So the derivative of, so it's going to be k n times the derivative of all of this. So we're going to have 1 over n times natural log of n minus natural log of k minus 1. That's going to be the derivative. And the derivative, we're going to take this resulting derivative and set it equal to 0. And when we set it equal to 0, we can now multiply out all the terms. So this is going to be n log n times n log nk minus n is equal to 0. If we divide it by n, we're going to get log n minus 1 is equal to natural log of k. We can exponentiate both sides because we can do that. If you have two things are equal, then e of those powers are also going to be equal to. So we have e to the natural log of k, e to the natural log of n minus 1. E to the natural log of k is just equal to k. And e to the natural log of n minus 1 is e to the natural log of n times e to the minus 1, which is equal to e to the minus 1 is 1 over e. So therefore, this is equal to e to the natural log of n, which is just n over e. So what we have here, and again, I don't expect you to do that, but if I give you, for example, now, so if I give you this type of formula, you should be able to do it. So what we have here is k has its maximum point when n is divided by e. So now, what we're going to do is, so it's a very simple result, fortunately for us. If we take a value, for example, let's say we're going to interview 20 people. Let's make 25 people. Let's take 25 people, and we're going to take, so that's for n is 25.